Good morning, class. This is March the 16th. I'm up here at school trying to get some last-minute videoing in so I can work with y'all on some of the skills we're focusing on this week. So today, real quick, we're going to focus on how to notate different bond forms when we're drawing these Lewis structures for different compounds. So, different textbooks have certain variations on how we look at ionic, polar, and nonpolar bonds, but I'm going to have us focus on the kind that I'm showing today, which I think is a really good way of doing it because the way they are drawn are very distinct from each other. There's no mistaking what type of bond you're looking at. So first of all, we want to look at page 308 in our textbook. This has the Pauling chart, which is a chart of the electronegativity ratings of different elements. You'll see that calcium here has an electronegativity of 1, chlorine has 3.16, carbon has 2.55, oxygen is 3.44, and nitrogen has 3.04. So what does that mean in terms of looking at what type of compounds we have? We use the electronegativity difference standard to determine what type of a bond we're looking at between two atoms. This value varies. I've seen ionic bonds to be those where the electronegativity difference between two atoms is as low as 1.7 or as high as 2.1, 2.2. I'm going to take a middle value, 2.0. That's what we'll use for the purposes of this week. Polar covalent is where the electronegativity difference between two atoms is significant, but not as great as ionic, between 0.5 and 2.0. And nonpolar covalent is where the electronegativity difference is quite low, or in the case of oxygen, where one atom is bonded to itself, it's 0. So what is the point of all of this? The point is that the types of bonds tell us very much about how a compound will behave, how it will react, what it will dissolve, what it will dissolve into, and many more other things that are important in our understanding of chemistry and chemical reactions. Ionic substances, as we know, tend to have very high melting points, high boiling points. They conduct electricity in solution very well. They're very brittle. They usually need metal, non-metal. And when we get to polar, we have substances like the most well-known, water, which most ionic compounds will dissolve into because they both have significant electronegativity differences, ammonia, and many other things. When we get to nonpolar substances, we're thinking of fats, oils, waxes, elemental forms, diatomics, oxygen, hydrogen, nitrogen, and so forth. They do not interact well at all with polar. As you've always heard, oil and water don't mix. That is because of their polarity character. And then we have some very versatile chemicals that have both nonpolar and polar characters. So let's take a look at how we draw these. So if we look at calcium and chlorine, we see that we have an electronegativity difference of 2.2. So we denote this by using dots around the electronegative one, showing they have an octet and that the valence electrons of the other have been captured by it. This is not a sharing of electron pairs in an orbit. We also denote with charge symbols this ionic character. That calcium, as we know, is an alkaline earth metal. It has a positive 2 charge. He loses his 2 electrons to the chlorides. When we move over to polar substances, such as ammonia, we will see that we have an electronegativity difference between hydrogen and nitrogen of 0.8. The more electronegative element gets a negative dipole symbol, and the more electropositive gets a positive dipole symbol. So we show the covalent line showing that our electron pair is being shared, but electrons are kind of spending more time over on the electronegative atom. we get to nonpolar. This is the simplest. We simply show shared covalent bonds. Oxygen, being a group 6 element, needs to form 2 bonds. So when it does with itself, it always comes in pairs, like our other diatomics, hydrogen, fluorine, chlorine, and so forth. Their electronegativity difference, once again, is 0, so we simply show covalent bonding and no further symbols. When we get to complex molecules that may have polar and nonpolar character, we denote them accordingly. Ethanol, like all alcohols, has a nonpolar hydrocarbon side. That the electronegativity difference on this end is very low between hydrogen and carbon, 0.35, putting it in the nonpolar covalent category. But over here is the polar side, this hydrogen bonding between oxygen and hydrogen, which allows it to interact with nonpolar substances. We have an electronegativity difference of 1.2. So we show those dipole symbols, more electronegative, less than electronegative, but still a covalent bond line. So in short, this is how we denote the 3 types of bonds: ionic, polar, nonpolar, and substances that may have more than one type of bonding form in its complex structure.